This chapter is about reasoning and decision making. Um, this is a another very broad and active area of research in cognitive psychology. It's an important area of research. As a matter of fact, there's a man named Daniel Kahneman who is mentioned in this chapter, where he was awarded a Nobel Prize for his work in decision making. So he's like really one of the only few people that might be considered experimental psychologists who have won a Nobel Prize for their work. And it was all related to how people make economic decisions. Um, then we're going to talk about the basics of reasoning and decision making in this chapter. Whenever you want to learn about reasoning, two of the broad categories of reasoning that you have to understand are the difference between deductive reasoning and inductive reasoning. In deductive reasoning, um, arguments go from general information, general principles, general conditions to a specific conclusion. So, for example, if A equals B and B equals C, then A equals C. That is a very simple example of deductive reasoning, where the end result of the argument follows from the premises that you presented earlier. This is the type of reasoning that is used, for example, by Sherlock Holmes. Sherlock Holmes will basically go through when he's trying to solve a crime, go through and systematically rule out who didn't commit the crime. He'll go each step by step ruling out who didn't commit the crime, and then that leaves him eventually with one person who he couldn't rule out. Therefore, that person committed the crime. Deductive reasoning is used by investigators, police investigators, also by, for example, the Federal Aviation Administration has crash investigators that make very heavy use of deductive reasoning. When they're trying to investigate the cause of a crash, a plane, they go through and rule out things. They rule out, certain type, engine failure, terrorist attack, whatever it is. They rule things out until they've gotten down to are some probable causes that they can work with. Inductive reasoning is where you make a conclusion based on prior specific instances. So, for example, um, one of the classic examples of inductive reasoning is the sun will always rise in the east and set in the west. Uh, if you don't know anything about astronomy and cosmology and whatnot, that is a very um, simple example of inductive reasoning, because as long as you've been alive, the sun has always risen in the east and set in the west. It's never risen in the west and set in the east or in the north. It's always been the same. So since it's been the same all those times in your life, you conclude that tomorrow it will rise in the east and set in the west. You have no logical premises for that if you don't, like I said, if you don't know anything about astronomy and cosmology and physics. But if you're just observing the behavior of the sun, and you conclude that it's always going to rise in the east and set in the west, that is an example of inductive reasoning, where you're simply making a conclusion based on some specific prior examples. Let's take a closer look at deductive reasoning. Deductive reasoning is evaluating arguments from a logical set of rules or principles. One of the earliest examples of deductive reasoning was that was given to us by Aristotle, and that's syllogistic reasoning. This is basically where the conclusion follows from a set of premises that you state. So you state a set of premises and the conclusion follows. So all A's are B's, all B's are C's are the two premises. Therefore, all A's are C's. So if A equals B and B equals C, then A equals C. That's syllogistic reasoning. All ants are insects. All insects are animals. Therefore, all ants are animals. This was the type of reason, like I said, this is the type of reasoning that Aristotle introduced formally, I guess, in his work. And it's a very basic, fundamental form of reasoning that works well with a lot of things. Conditional reasoning is a more formal type of reasoning. It is sometimes called propositional reasoning. It's basically where a conclusion follows from a set of conditional statements. So, you say, if P, then Q, right? So if condition P exists, then Q. If condition P does not exist, then not Q, right? They're very specific, like almost like a program, but really it's a set of conditions that are explicitly defined that lead you to a conclusion. If you know anything about math theorems, for example, like proving a theorem or developing a theorem in mathematics, theorems are entirely based on conditional reasoning. They lay out a set of conditions, and the mathematician will work through and build those conditions to reach whatever conclusion that he or she is looking for. There's a simple example of conditional reasoning in your textbook. It's a little bit hard to understand. So this example is on the bottom of page 322, and it's Wason's 4-card task. And basically, here's the problem. So the statement is given as follows: if a card has a vowel on one side, then it has an even number on the other side. Now, we want to assess whether or not this statement is in fact true. And how can we assess that statement? By only turning over two of the cards that you see listed at the bottom of page 322. So you have 4 cards. You have an A, D, 4, and a 7. And remember that behind that card is going to be another letter or number. And we want to only turn over 2 cards and prove that if a card has a vowel on one side, then it has an even number on the other side. Well, the solution is given at the bottom of page 323, and let's take a quick look at that. And it's a little hard to follow. You kind of have to think about it, but let's look at the 2 wrong cards, right? The two cards that you would pick are going to be A and 7. Well, let's look first at the 2 cards you wouldn't pick, D and 4, and why you wouldn't pick those cards. Well, if we look at D, right, the D card, that card right there starts off by being a not a vowel. So it's a consonant. So right there, if I were to pick that card up and flip it over, and it let's say it had an even number, let's say it had a 2, right? That would not disprove the simple statement that if a card has the vowel on one side, then it has an even number on the other side, right? It wouldn't disprove that at all. It would just mean that if a card has a consonant on one side, it has an even number on the other side, right? I mean, so flipping that card over would be of no help whatsoever. And the key to that is by the fact that it's the letter D. It's a consonant, so you're starting off with a not vowel. So since I'm looking at that card and it's like it's not even a vowel, that's not going to help me. It doesn't matter what I see on the other side. Whether it's an even or an odd number, that's not going to disprove anything because it's not even going to refer to a vowel. So that card is useless. The second card is a 4, so we can assume that it's flipped, and for the same reason as the other one, almost, even though it says a 4, If I were to flip that card over, and let's say it was a consonant, again, that wouldn't prove anything, because that would just be saying if a card uh, is not a vowel, then it'll have an even number. That doesn't disprove that if a card that doesn't disprove the statement. If a card has a vowel on one side, then it has an even on the other side. However, let's look at the correct answers, right? So here is card A. Now that card has a vowel, right? It's got the vowel. So I flip that over. If it has a vowel on one side, it will have an even number on the other side. If I flip that card over and it does not have an even number, bang, I've disproven the statement right there. If it has an odd number, I've disproven it. So that card is very helpful in evaluating the truth of this statement. Similarly, the other card too, the 7 card, is also very helpful because that's an odd number. There cannot be a situation where a card has a vowel on one side and an odd number on the other side, right? So if I flip that card over and I see a vowel, I've just disproven the statement, right? So that statement is incorrect. But if I flip that card over and I see a consonant, I've proven it. I've proven that the statement is correct. If a card has a vowel on one side, it's got an even number on the other side. So the 2 cards that will help you in determining the truth of the statement are the A card and the 7 card. The 2 cards that won't help you logically are the D card and the 4 card. So here's an example of some syllogisms that are a little difficult to evaluate. The first one is all beagles are dogs. Okay, got that. Then we can also say all beagles are mammals. Okay, so all A's are B's and all A's are C's. So A equals B and A equals C. Therefore, all dogs are mammals. Does the conclusion all dogs are mammals follow logically from the 2 statements all beagles are dogs and all beagles are mammals? Well, it doesn't. It doesn't, because we've got that thing in the middle, beagles. And the conclusion doesn't lead or connect well from the premises about beagles, right? You can't say all dogs are mammals just because all beagles are dogs and all beagles are mammals. There's nothing in that statement that would say that all dogs are mammals, because you could have another statement in there that says, all cockroaches are dogs, right? All beagles are dogs, and all beagles are mammals. Um, Therefore, all dogs are mammals. That would also be completely invalid. The second one is also the second one, B. All beagles are dogs. Okay. All beagles are mammals. Some mammals are dogs. Now, this is logically consistent. This is actually true. It's hard to see because the 2 premises are all and all, but then the conclusion is some, right? So all beagles are dogs, all beagles are mammals. Therefore, we can conclude that some mammals, not all mammals, but some, the opposite of all is some, some mammals are, or one of the opposites of all is some, I guess, some mammals are dogs. Okay, so that actually makes sense. That actually is true. The other one is also true, but it's really hard to see. No elephants are insects. Okay, because now we have a negation. A negation where you say no P or not P. That makes um, arguments, syllogisms, or deductions a little bit harder to see. But no elephants are insects. Okay, so no elephants are insects. All insects are animals. Okay, so no elephants are insects. all insects are animals. Some animals are not elephants. Okay. That conclusion does logically follow from the two statements. No elephants are insects, and all insects are animals. Therefore, some animals are not elephants. Again, it's hard to see because we have a negation, we have an all, and we have a some. And working your way through those types of arguments is a little bit tough. Here's another one, right? This is table 12.2, right? So if it is sunny outside, then I will walk to class. It is sunny outside, therefore I will walk to class. So if P, then Q, right? So that's a real simple one. It's like the first card in the card task that we saw. If P, then Q, right? So if it is sunny outside, P, then I will walk to class Q. If it is sunny outside, then I will walk to class. I will not walk to class. It is not sunny outside. Okay. This is also valid, and it's like the 7 card in the card task that we saw earlier. If it's sunny outside, then I will walk to class. So I'm not going to walk to class. Therefore, it must not be sunny outside. So if it's C, if it is sunny outside, then I'll walk to class. If P, then Q. It is not sunny outside, not P. I will not walk to class. Then therefore not Q. That's also valid. If it is sunny outside, then I'll walk to class. I will walk to class. It is sunny outside. Again, if I will walk to class. It is sunny outside. Uh, Again, that is also valid. But a lot of people that look at these don't get them right. It's really hard to, you know, uh, based on this sort of deductive conditional reasoning. So there's lots of general approaches that have been specified for deductive reasoning. One of them is the conclusion interpretation approach, and this is where basically errors that we make in our conclusion come about from general biases against making particular conclusions. For example, some ants are insects and some insects are ants. Okay, those are logically equivalent. Uh, and so we might think all ants are insects and all ants are insects and all insects are ants. We might think that that might be correct, but it's not. That is not a logically valid conclusion. And the reason we might think it's correct is because um, we thought we could switch ants and insects in the some statement. So some ants are insects, some insects are ants. Switch them around. Oh, we can do that all the time. But if we try it with all ants are insects and then all insects are ants, that doesn't work. We have to make sure that we're careful when we're evaluating arguments like that to make sure that we aren't reaching an incorrect conclusion because of some bias that we inherited earlier. I think one of the and this of course can lead to some awful problems when people refuse to see something that they don't want to see. When the back in the 1986, when the Russian nuclear power plant exploded at Chernobyl, um, the the people on the ground, the directors on the ground, just refused to believe it because the type of reactor design that they used weren't supposed to explode. But those types of reactors weren't. There was no. They didn't think there was a physical way they could explode. And that was just because of all the their prior experience with that type of reactor and what they thought they knew about that reactor. And so whenever they had people coming and telling them, "Hey, the reactor exploded, the core is like gushing radiation out into the open air," at first they weren't believed. and and that was because of this bias they had toward reaching particular conclusions about what happened. Representation explanation approaches uh, focuses on how we represent arguments, how we represent the different types of conditions and the different things that go into making a particular conclusion. For example, one of the big uh, factors in how we represent arguments has to do with the difficulty. Uh, the type of reasoning, if we have reasoning that requires lots and lots of complex rules, lots and lots of chaining together a bunch of rules, and that puts real demand on our working memory. And so therefore, we're probably not going to do so well on those types of problems where there's a lot of complex factors that need to go into understanding a particular conclusion. We have different theories for how we represent different the premises and arguments. The mental logic theories that are mentioned in your book propose that, or say that our deductive reasoning proceeds by applying a set of rules, right? So we basically have a bunch of rules, general rules that don't depend on the particular situation or context. Uh, and we just have these general propositions that we follow. Um, when we're making sort of the day-to-day types of reasoning. Surface approaches talk about reasoning that relies on general heuristics. So remember, general heuristics are like those rules of thumb, general guidelines that are focused on the surface properties of the quantifiers in the argument. So um, instead of instead of applying some set of rules, propositional rules, like in representation explanation approaches, we instead of reasoning analytically like that, we look at the general. We take each condition in an argument and just evaluate it on its own, looking at the properties of that and seeing if the properties of each one of those particular premises or arguments makes sense or goes together with the other premises. So, for example, if you have an argument that contains premises, like universals, like that says all or none, if you have an argument that has a bunch of statements like that, then the conclusion that you reach is probably going to be something that has a bunch of universal statements like all or none. If you have arguments that contain negative premises like a no or a not, like a negation, then the conclusion that you reach is probably going to be negative or negative sounding. So each one of these reasoning approaches has been proposed as sort of a way that we uh, do deductive reasoning. So here's an example of a mental model approach. And basically it takes the two premises, all ants are insects and all insects are animals, to reach the logical conclusion all ants are animals. There's a typo there in at the top of figure 12.7. The conclusion says all ants are insects, and it should say all ants are animals. So that doesn't make any sense the way it's written. So for step one, we construct a model, and these are set diagrams. If you don't know anything about SET diagrams, you might want to look that up. So basically, model one, all A's are B's. I prefer the diagrams that are on the left-hand side of the or, because you could represent them either way. So basically what the first one says is that all instances of A can be categorized as an instance of B, right? So A is inside the B circle. The A circle is inside the B circle. So all A's are B, right? So all ants are insects. And then all insects are animals. So insects is B, if you remember, and all insects are animals, C. They're all encompassed in the category C, right? So all ants are insects, and all insects are animals. So then we formulate our conclusion, right? And one of the things that we can do is to combine those diagrams, right? So put them together. And if you go ahead and put them together, by overlaying them on top of each other, you end up with the one I prefer is the one that is at stage 2, the one that is the second from the left, where C is all animals, right? B is all insects, and A is all ants. So we can see from this diagram that all ants are insects. And then we can see from this diagram also that all insects, all bees, are also animals. And then step 3, or stage 3, I should say, is the conclusion validation. So to evaluate to go to all A's or C's, or all ants are animals, we can basically remove the B. And if we can remove the B and still have the A and the C contained with each other, then we can say that we have a valid argument. So if you look at the bottom on stage 3, and if you look at the little set diagram there, or the Venn diagram on the right hand side, you'll see that we took away the B. We took away category B, which in this example would be insects, and we're left with ants being a condition of animals, or ants being a subset of animals. So to put together all of this, when do we use deductive? When do we use inductive? Well, we use both. We have two, processes that we use in this and so there's been this theoretical framework put together called a dual process framework that includes two basic types of reasoning. Um, uh, System 1 versus System 2 processes. The System 1, System 2 processes are defined here in Table 12.3. So System 1 processes are unconscious and preconscious. So these are the sorts of things that we sort of do on autopilot. We do these things automatically. They're unconscious, they're rapid, they're automatic. Doesn't require any effort for the most part. We can do a lot of them. High capacity. We can, we do System 1 reasoning all the time. When you're driving, walking, talking to people, you're constantly doing that. It's associative, meaning that you get the ability to make these System 1 types of reasoning from experience by associating events and your experiences. It's intuitive, meaning you don't have to think about it. It just comes as a reflex. It's contextualized. It's based on the particular place and time that you're at. There are lots of cognitive biases associated with this type of reasoning. For example, stereotyping. And it's independent of cognitive capacity. In other words, you don't have, you can be really tired or really rested, and it really doesn't matter. Your System 1 unconscious reasoning abilities aren't going to be affected that much. System 2 is our reasoning abilities that are associated with conscious, effortful thought, the things that we have to do. It's slow. You have to work through it. It's controlled. You have to actually engage in actively going through the steps. It's not automatic. It requires a lot of effort. It's low capacity, meaning you can only do a few decisions at a time. Rather than just being the result of associating your experiences, it is rules based. You are going through some set of rules, whether it's follow the evidence or follow the logical conclusions, whatever it is, you're going through some set of rules. It's not intuitive; it's deliberative, where you have to actually engage in thought. It's an abstract sort of ability that transcends time and place. So you can use System 2 reasoning skills no matter where you're at, whether, where, for any type of. There's normative reasoning. In other words, System 2 logically allows you to rule out biases, to systematically rule out biases. And it is, based on individual differences. There are some people that are really good at this and some people that aren't so good at it. Let's talk a little bit about inductive reasoning. Deductive reasoning is about reaching an absolute truth, an absolute single uh, statement, single conclusion based on a set of preferences or preconditions and premises. Um, the thing about deductive reasoning is, it's very powerfully used in areas of mathematics and cognitive science and computer science and solving theorems, and so that's what it's for. That's what it does. Inductive reasoning, on the other hand, really is allowing you to reach conclusions about a likelihood of something being true based on your prior experiences. So it involves reasoning from some specific experience, some specific data to broader generalizations. One of the really useful things that inductive reasoning is used for is to generate new information. You can't necessarily generate new conclusions from deductive reasoning, because deductive reasoning necessarily follows from stuff you already know. Um, so, being able to see new things is, you can do it, but it's going to be limited based on the context. One of the good things about inductive reasoning, one of the uses of inductive reasoning, is to sort of get some insight to making new conclusions um, from information or from prior experiences, generalizing from prior experiences. There are different types of inductive reasoning. One of them is analogical reasoning. This is where you're, reasoning by analogy. So, Forrest Gump, life is like a box of chocolates. So you never know what you're going to get. Um, this is, taking an analogy and applying it to a particular, to another situation or another condition. So this is a very, very powerful, actually, very powerful way of reasoning. It's a very powerful way to do creative thinking. Another type of inductive reasoning is category induction. So, if you see, if you're walking around and you perceive this large metal object going down a street, then you categorize that as a car. And since you put that large thing going down the street, since you categorized it as a car, you can make a lot of assumptions about it. So if you could hear its engine and see smoke coming out the back, it probably runs on gasoline. You know that it costs a lot of money. You know a lot of things about it just by categorizing. Causal reasoning. One of the things that we do in causal reasoning is we try to infer causes and effects. One of the things that our brains naturally do is to infer causes and effects. Two things that go into inferring causal relationships are beliefs and covariance. So a belief is what you think is causing something, and covariance is, did you see the two things happening together? Did you see things happening together? If you have a belief about what causes something, and you have covariation where you see these two things happening together, you're going to put that belief along with those two things happening together into a causal relationship. You're going to say that those two things happen together because one caused the other based on my belief. Um, of course, as you know, people can have wrong beliefs about things. We have a lot of human-caused global warming deniers out there because they have incorrect beliefs about uh, uh, um, the causal relationships in climate. And also covariation, is tough too because, you know, two things that are caused by each other may not obviously be covariant with each other. It may not be immediately obvious. Hypothesis testing is where you're given a problem and you generate solutions to do essentially one of two things: to verify the truth of the way you think something works, or to falsify. In other words, come up with find a way to falsify or figure out a situation where um, something is inconsistent with a particular conclusion. Uh, your book goes through some examples of an experiment where people are given a sequence of numbers, and their job is to identify the rule that was used to generate that sequence of numbers. So, for example, if I give you 246, um, one of the things you might say is the first three even numbers that are greater than one. That's a pretty simple thing to do, right? But then as the number sequences get more and more complex, you're going to start coming up with different uh, ideas for what was the rule that we used to generate these numbers. And you're gonna engage in hypothesis testing. You're gonna come up with your own sets of numbers to verify the rules that you come up with and to falsify the rules that you come up with. Counterfactual thinking is one of my favorite topics. It's actually, sort of the what if, so man, I failed that test, but, if I would have just studied more, I would, made a better grade. That's an example of counterfactual thinking. That sort of reasoning where we, do engage in this sort of, if only, what if, going through this, scenario of saying how a particular situation would have been different. So one of the questions you want to ask about this sort of research, where we're having people work on all these problems to understand reasoning, is what is the external validity of this type of research? In other words, is it valid in real life? And we can compare laboratory reasoning tasks with everyday reasoning. So, in a laboratory task, all the premises are supplied for the most part. In everyday reasoning, some premises are implicit and some aren't supplied at all. For example, what um, what what is the best career option for you, right? For example, there's going to be some premises that are very implicit, what your interests are, what your skills are, but then there's going to be a lot that aren't. There's a lot about the future that you don't know. The problems in the lab are self-contained versus, in everyday life, the problems are not self-contained. Problems are connected to other problems and other situations. In the lab, there's typically one correct answer. In everyday life, there's typically several possible answers. This is actually a really important lesson for a lot of you. Most of you are, just 1 or 2 years out of high school. And, one of the things that I have found with very young undergraduate students is they really have a hard time with this. That in college, sometimes there's more than one correct answer, and we're not, professors aren't necessarily looking for the correct answer because you've been conditioned up to this point, from grade 0 through high school, to supply the correct answer, and life doesn't work that way. If you keep thinking that way, you're just going to end up, not being very successful. In the lab, established methods of inference. The lab uses established methods of inference that apply to the problem. Um, in real life, not necessarily. There's rarely established procedures for solving problems. Sometimes there are, but for the most part, there aren't. You just kind of have to, figure things out step by step. In the lab, it's typically unambiguous when the problem is solved. In other words, you know when you got the right answer. In real life, it's often unclear what the current best solution is, or when you hit the point of it being good enough. You don't know when to stop. The content of the problem is of limited academic interest. Basically, the problem that you solve in the lab is typically, not that grand in the scheme of things, right? It's really only has to do with the lab, but um, in everyday reasoning, the problems that you're solving are relevant to you. They're important to you. And that's that is probably going to change your motivation and the resources you dedicate to that problem. And then finally, problems are solved for their own sake versus in everyday life, the problems are really part of achieving other goals. So problems are really contained within bigger problems that are ultimately linked here. Making decisions, the art of making decisions has to do with assessing and making choices between different options. Um, your book outlines this general model of decision making where the first thing you have to do is set goals. Okay, if you're making decisions, you got to say, okay, well, what are my choices? What is it that I'm looking for? Then you gather information related to those goals. You organize that information into some sort of structure, some sort of framework that makes sense so that you can evaluate all of the information. Then you make the final choice, and then you evaluate your choice. Was it a good decision or was it a bad decision? Ideally, one of the things that ideal decision making is based on a careful consideration of the facts. And one of the classic examples that is always given is this decision uh, as to which purchase to make. The example that's given in your book is um, you know uh, which computer to buy, right? So, we have these different criteria, right? Portability, power, hard disk space, work potential, gaming potential, how cool it is, the price, and the screen size. We rank those particular criteria on how important they are to us. So, in this example here, price is the number one consideration. The second consideration is using it for work. The third one is computation power. The fourth one is portability, etc. And then we go through and we list for each one of these criteria, we list out how each one of our options reflects that criteria. And we score it, high, medium, low, 1, 2, 3. So for example, the first laptop scores high for portability, which is a 1. The first laptop scores a 3 for processor speed because it's a 2.8 gigahertz, whereas the fastest one is 3.2 gigahertz, so that's faster. That's a 1. The first laptop listed there scores a 2 for hard disk space. Anyway, you take all of those, you take the score and then you multiply it by the importance, and then you add those things together. So for portability, for the first laptop, importance is 4, and it scored a 1, so 4 times 1 is 4. Computation power, importance was 3, and it scored a 3, so 3 times 3 is 9. Hard disk space, importance was 5. The laptop scored a 2 on that, so 5 times 2 is 10. You add all those up, and you come up with these numbers. And you end up with these numbers, with these weighted numbers that are weighted as to, based on how important each one is to you. And you add them all together, and the lowest, in this example here, the lowest number is going to be the best number because a 1 means really good and 3 means like sucky. So the higher the score, the more sucky the particular model is. So based on everything that is here, um, this person would decide to purchase the desktop computer based on the evaluation here. And again, this is an example of ideal decision making where you systematically uh, define what your goal is, lay out all of the qualities, rank order them, score them, and then come up with make a decision based on the final scoring. Heuristics are, if you remember, we talked about algorithms and heuristics. Algorithms are these step-by-step procedures, recipes for solving problems. However, heuristics are not like algorithms. Heuristics are mental shortcuts, rules of thumb that we use to reduce the processing burden of our cognitive systems. Um, Heuristics are faster than like lumbering through an algorithm. They require fewer resources, and they usually, not always, but usually give the right answer. However, heuristics, since they're fast, and their shortcuts, they often ignore information. As a matter of fact, when you're using heuristics, you often end up at the mercy of certain biases that are related to the use of your that are related to your use of heuristics. The I always have trouble saying this word. The representativeness bias is basically a bias that says it's basically like a stereotype bias where you see you see a particular person or a particular situation and you automatically stereotype or make an assumption about that person or the situation based on what you see that it represents something that you're familiar with. So if you see so if you see a guy who is poorly dressed, doesn't dress well, with thick glasses, and is always looking down, and isn't doesn't really talk to anybody, and is holding a computer, um, and is wearing like an anime shirt or something. You might assume that, oh, that person is a total geek, total nerd, and they're probably introverted, and they're probably good at math, and they're probably not very social, right? You're making that uh, that conclusion using a heuristic based on your representation of a particular type of person. The availability bias is the bias that we have when we're making decisions. That essentially it says that our decisions are based on the information that we have. We're going to use the information that we have available. And if we aren't aware of that, we're going to make a decision that may not be the correct decision simply based on what we have available. For example, usually when if we ask the question, what is the number one killer of women in the United States? And the number one thing that women die of in the United States, what a lot of people will say is breast cancer. And breast cancer is actually fairly low on the list. I think the number one killer of women is heart disease. It's the number one killer of men and women. Is heart disease. But the reason people say breast cancer is because breast cancer receives a lot of media attention. There's the walks and the pink ribbons, and there's a lot of there's a lot of attention around breast cancer. So people assume that that's like a big killer of women because of this availability bias. Fox News is entirely, based on availability bias. The people that make their, political decisions and just watch Fox News are going to be making very different decisions because, they're the only information they have available is the very biased information they're getting from Fox News. The framing bias says that conclusions that we reach on a particular problem are going to be based on how the problem is framed. Um, you Classic example is, if okay, I can either sell you one bottle of soda for a dollar, right? Or if I say, if I price that would mean each bottle of soda is a dollar, right? So it's, three bottles of soda would be $3, right? Believe it or not, people are going to actually buy more soda if I frame it to say both bottles of soda, each bottle of soda is $1.50, and if you buy two, if you buy two, you get one free, right? In both cases, you're spending $3 to get soda, but the way you framed it makes it sound much more attractive. Uh, and you assume that you conclude that you're saving money or getting a better deal uh, with the buy two at 150 get one free versus just buy three for uh, a dollar each. They're both the same amount of money. You lose the same amount of money, you get the same thing, but um, the buy two get one free results in more sales because of this framing bias. It turns out we use a lot of different decision making strategies really based on the context. We don't use one set of strategies for everything. Um, Tversky was one of the first to talk about this, and he talked about this elimination by aspect strategy. Um, Basically, what we do here is we limit the number of criteria that we're considering when we're making a decision. Uh, so we only consider the most important ones, right? So, for example, when you're buying, if you're making a big buying decision, like you're buying a house or a car, right? Probably the number one important consideration for most people is going to be price, right? I mean, but maybe price, and if you're buying a house, school district, or price and uh, maybe uh, the deal that you get from the bank, the loan. You don't consider everything, right? Because buying a house or buying a car, it's a very complex process and has a lot of moving parts. So you really only focus on the top, aspects that are most important when you're making a decision. Um, C in 2000 talked about this decision making approach where we focus really not so much on the most important aspects, but really on the criteria that are easiest to evaluate, right? So there's some things that are easy to evaluate, others that are not. Um, Price is one for when you're buying a house, right? For the most part, the price is the price, and you negotiate, and you can get it down if possible, but for the most part, the price is the price. When you're buying cars, price, the price that they quote you is not the price that you're probably going to end up paying. Price is hard to evaluate when you're buying a car. I mean, you have a general range, but then they start throwing a bunch of things at you, and you're like, oh my god, what's the ultimate price going to be? So you focus on other things that are easier to evaluate, right? You have a general idea of what the price is, but you focus on things like the quality of the car, the dependability, the way it looks, whatever, right? Those are more easier to focus on. We certainly do use past experiences when we're making decisions. So Daniel Kahneman, the guy that I mentioned earlier that won the Nobel Prize for his ideas on decision theory, came up with this really fundamental notion of prospect theory. And basically, what prospect theory says is we evaluate things differently based on whether they are gains or losses. So, in other words, um, take for example, decisions where you're going to gain $100 or lose $100. Well, we evaluate losses much more severely than we do. Right? We consider losses, or we make decisions to mitigate losses as opposed to make decisions to gain more. So our decisions are really going to be based upon loss mitigation as opposed to uh, gaining things. And it's a bias that we um, uh, losing $100 is much more of an impact on your life than gaining $100 in this theory. And obviously, that $100 is going to be related to what you're starting with. If losing $100 is going to matter a lot more if your bank account has $105 in it versus if your bank account has $1 million in it. If your bank account has $1 million in it, well, losing $100 is like no big deal. But if you have if that's like the most of your bank, then that that conclusion is obviously going to have much more an effect. You're going to be making decisions to minimize that as much as possible. So the dual process framework that we discussed earlier has been proposed for helping us to understand why it is that we sometimes make, logical, rational decisions and sometimes we don't. Because essentially we use a lot of different methods to make decisions based on the context. So your book talks about an experiment by Wilson and Schooler where people are selecting varieties of jams, jam, like jelly or jam. Sometimes the subjects in the study used system 1 type reasoning, this unconscious inference, and sometimes they used system 2 type reasoning. So, if the students were told that, if the students were like informed about, what the experts said about the jams, then they would use more system 2 type reasoning. But if the students were just sort of like tasting it on their own, they would use more system 1 type reasoning. So, really the future of decision making is going to be a very complex sort of thing. I think for the most part, it's going to involve not only psychologists, but also neuroscientists, economists, etc. So the study by Dinez that's mentioned in your book on page 342 and 343 is an example of bringing together some psychology and neuroscience. So it's a little bit of a complex study. So, but the behavioral results are shown in figure 12.11 that's seen on this slide. So the first bar that you see there is the bar for congruent control. And by congruent, we mean that the correct answer to a question that was asked by people is related to both the base rate and the stereotype associated with that particular situation. The base rate has to do with the representation of biases in a particular group or population. So for this first bar here, one of the things that they did was they got 5 Swedish people and 995 Italians. So 1,000 people together, but 99.5% of them were Italian, which means that the base rate of answers that come out of this group are going to be heavily biased toward Italian culture. And then they presented them a problem that contained a stereotype. And the problem is given under congruent control in table 12.5. So there's Marco is 16. He loves to play soccer with his friends, after which they all go out for pizza or to someone's house for homemade pasta. That's a stereotype. And when the stereotype is congruent with the base rate, in other words, when the stereotype is congruent with, however many biases are presented in the population, that's known as a congruency. So it's a congruent control group. And if you look at the data in figure 1211, you'll see that close to 100% of people got the right answer. And then for the second bar, heuristic control, we have an evenly divided group. In this case, it's 1,000 people, but 500 are 40-year-olds and 500 are 17-year-olds. And the problem that they were given was Ryan lives in Buffalo. He hangs out with his buddies every day and likes to watch MTV. He's a big Korn fan and is saving money to buy his own car. Which is most likely? Ryan is 40 or Ryan is 17? Um, this is using a heuristic, a stereotype heuristic, right? Because the description is entirely stereotypically based. It is, uh, 40 or 17. And so the Q is given as the age, right? So it's I'm sorry, the problem is given as a stereotype. So in that example, again, most people got the correct answer, right? 100%. And also, most people got the correct answer in the third condition, the neutral control condition, where you have basically a study with 5 people who campaigned for Bush and 995 people who campaigned for John Kerry back when he ran against George W. Bush. Um, then they give a problem, whether or not that's very neutral sounding. Jim is 5'8", has black hair, is the father of 2 young girls. He drives a yellow van that is completely covered with posters. And it turns out that what they're going to do is they're going to give an answer that's based on their base rate. So it's going to say, oh, that sounds like me. That sounds like one of my people. And sure enough, that's what we end up with. We end up with this the base rate queued answer is the correct answer in this example, and sure enough, it comes up on top. However, if we look at the last condition, condition 4, the incongruent condition, we have 5 engineers and 995 lawyers. And so we have Jack is 45 and has 4 children. He shows no interest in political or social issues and is generally conservative. He likes sailing and mathematical puzzles. When we give them 2 incongruent answers, one that is stereotype cued and one that is base rate cued, people are going to evenly choose between one or the other. Sometimes they're going to go with the stereotype, and sometimes they're going to go with the base rate approach, which, okay, well, I'm a lawyer, so I think he sounds like a lawyer. Or they're going to go with, this kind of sounds like it might be an engineer. I'm going to go with an engineer. This tells us, again, that the decisions that we reach, the conclusions that we reach based on people are going to be very heavily dependent upon not only not only the facts that are given to us, but also the context, the stereotype context, as well as the our personal biases. The other interesting part of this study is they looked at the brain while people were making these decisions. They used the functional magnetic resonance imaging to look at the right lateral prefrontal cortex, which is really in the right lateral prefrontal cortex has been linked with response inhibition. So whenever our brains are telling us not to do something, that cortex lights up. Essentially, that part of the cortex lights up. And they also looked at the anterior cingulate cortex, that is that seems to be involved in conflict detection. So whenever there's inconsistencies or conflicts detected, that part of the cortex becomes active while they were completing the task. Now the results that they got showed that when the participants in the incongruent condition, the incongruent control group, responded with their base rate cued answers, there was increased activation in their right lateral prefrontal cortex, which was reflecting the inhibition of a stereotype-based response. The activation was not present when they made a stereotype-based response. So the brain said, go ahead and make a stereotype-based response. So this is a complex study, but it's interesting because it gives us a little bit of insight as to the mechanisms that are involved in understanding how the different parts of our brain are regulating the ways that we're making decisions in these fairly complex areas. So here's a summary, right? For the congruent control condition, the correct answers were consistent with both base rate and stereotypic cues, right? Which is which is awesome. Whenever they got a base rate cue, they picked it. Whenever they got a stereotypic cue, they picked it. For the heuristic control condition, the correct answers were consistent with stereotypic cues. So if I were to give you like general heuristics, a problem that involved heuristic problem solving, you went with a stereotype, which is what you should do. For the neutral control condition, where I just sort of like made things kind of vague, the correct answers were consistent with either the base rate condition with the base rate condition. So if it was vague, you went with whatever you happened to be. For the incongruent conditions, in other words, where I mixed things up and I gave you two competing cues, one was a stereotype and one was a base rate based. Both answers were considered correct. One of them reflected stereotype cues, the other reflected base rate cues.